Black holes. Just the name conjures images of cosmic monsters devouring everything in their path. They are among the most fascinating and mysterious objects in the universe. These enigmatic entities continue to captivate our imagination, inspiring countless science fiction stories and fueling our curiosity about the cosmos. But what are black holes, really? How do they form, and what happens if you get too close? Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine the Earth squeezed into a sphere the size of a marble. That's the kind of extreme density we're talking about. This intense gravitational pull creates a cosmic abyss, a point of no return for anything that ventures too close. The very idea of a black hole challenges our understanding of physics and reality. They push the boundaries of our knowledge, forcing us to confront the limits of what we know and can observe. Yet despite their enigmatic nature, we have learned a great deal about these celestial objects. Through decades of research and observation, we have pieced together a picture of black holes, their properties, and their role in the universe. We have developed theories to explain their bizarre behavior, and even glimpsed the faint echoes of their existence through gravitational waves. Black holes are not cosmic vacuum cleaners, randomly sucking up everything in sight. They are born from the remnants of massive stars, stars far larger than our own sun. When these stellar giants exhaust their nuclear fuel, they can no longer support themselves against their own gravity. The core collapses in on itself, creating a supernova, a spectacular explosion that briefly outshines an entire galaxy. If the core is massive enough, the collapse continues unabated, crushing the stellar matter into an infinitely small point. This point, known as a singularity, is the heart of a black hole. The singularity is a place where the laws of physics as we know them break down. It's a point of infinite density and zero volume, a concept that boggles the mind. Surrounding the singularity is the event horizon, the boundary beyond which there is no escape. Once you cross the event horizon, you are forever trapped within the black hole's gravitational grip. No matter how powerful your spaceship or how hard you try, you cannot escape the inexorable pull towards the singularity. Imagine the event horizon as a cosmic waterfall. As you approach the falls, the current gets stronger, making it difficult to swim back upstream. Eventually, you reach a point where the water flows faster than you can swim. This is the point of no return. Similarly, the event horizon marks the boundary where the gravitational pull of the black hole overwhelms all other forces. Once you cross this boundary, you are inexorably drawn towards the singularity, like a raft caught in a raging river. Interestingly, the size of the event horizon depends on the mass of the black hole. More massive black holes have larger event horizons, extending their reach further into space. Some supermassive black holes, millions or even billions of times the mass of our sun, have event horizons that span billions of kilometers. But don't let the term horizon mislead you. The event horizon is not a physical boundary, like the surface of a planet. It's simply a region in space where gravity becomes so strong that escape is impossible. There's nothing to see or touch, just a point of no return in the fabric of space-time. The singularity at the heart of a black hole is perhaps the most mind-bending concept in all of astrophysics. It's a place where our current understanding of physics breaks down, where the very notions of space and time cease to have meaning. Imagine all the matter of a star, millions of times the mass of our sun, compressed into a point smaller than an atom. That's the singularity, a point of infinite density and zero volume. At such extreme densities, gravity becomes infinitely strong, warping space-time beyond recognition. Our current theories of physics, such as Einstein's theory of general relativity, cannot fully describe what happens at the singularity. We need a new theory of quantum gravity, one that unifies the macroscopic world of gravity with the microscopic world of quantum mechanics. Despite our limited understanding, we can speculate about the fate of matter that falls into a singularity. Some theories suggest that matter is crushed out of existence, its very essence destroyed. Others propose that matter might be transformed into some unknown state, perhaps even escaping to another universe. Section 5. A leap into the abyss, falling into a black hole. Let's indulge in a thought experiment. Imagine you're an intrepid astronaut venturing too close to a black hole in your trusty spaceship. As you approach the event horizon, you wouldn't feel anything special. No sudden jerk or jolt. Gravity, after all, is a force that affects everything equally, regardless of size or composition. You and your spaceship would simply fall freely towards the singularity, much like skydivers plummeting towards Earth. However, things would get strange very quickly. As you fall deeper into the black hole's gravitational well, you would experience time dilation. Time would slow down for you relative to observers watching from a safe distance. To them, you would appear to slow down as you approach the event horizon, eventually freezing in time at the very edge. From your perspective, however, time would continue to flow normally, albeit with some bizarre consequences. Section 6. Spaghettification, stretching beyond recognition. While time dilation might sound intriguing, the process of spaghettification is far less appealing. As you fall towards the singularity, the gravitational pull on your feet would be much stronger than the pull on your head. This difference in gravitational force, known as tidal force, would stretch your body like spaghetti. Your bones would crack, your organs would rupture, and your body would be elongated into a long, thin strand of matter. The closer you get to the singularity, the stronger the tidal forces become, eventually ripping you apart at the atomic level. Your constituent atoms would be torn asunder, their protons, neutrons, and electrons scattered into the abyss. The process of spaghettification is a gruesome reminder of the immense power of black holes. They are cosmic shredders, capable of tearing apart even the most massive objects in the universe, reducing them to their fundamental particles. Section 7. Time twists and paradoxical perspectives. One of the most mind-boggling aspects of black holes is their effect on time. According to Einstein's theory of general relativity, time is not absolute but is relative to the observer's frame of reference. This means that time can flow at different rates for observers in different gravitational fields. For an observer far from a black hole, time flows normally. But for an observer falling into a black hole, time slows down relative to the distant observer. This time dilation has some bizarre consequences. Imagine you could shine a flashlight back towards the distant observer as you fall into the black hole. The light from your flashlight would be stretched by the black hole's gravity, its wavelength becoming longer and its frequency lower. This phenomenon, known as gravitational redshift, would cause the light to appear redder and dimmer to the distant observer. Eventually, the light would become so redshifted that it would be invisible to human eyes. Section 8. Hawking radiation. Black holes aren't so black after all. For decades, black holes were thought to be inescapable cosmic traps, their gravity so strong that nothing, not even light, could escape their clutches. However, in 1974, physicist Stephen Hawking proposed a revolutionary idea: black holes are not entirely black. Hawking showed that black holes should emit a faint thermal radiation due to quantum mechanical effects near the event horizon. This radiation, known as Hawking radiation, arises from the creation and annihilation of virtual particle-antiparticle pairs near the event horizon. According to quantum mechanics, empty space is not truly empty but is teeming with virtual particle-antiparticle pairs that constantly pop in and out of existence. These pairs borrow energy from the vacuum, exist for a fleeting moment, and then annihilate each other, returning the borrowed energy. However, near the event horizon of a black hole, one particle of the pair might fall into the black hole while the other escapes into space. The escaping particle carries away some of the black hole's mass energy, causing the black hole to slowly evaporate over time. Section 9. The slow fade of a cosmic giant. Hawking radiation has profound implications for the fate of black holes. While the rate of evaporation is incredibly slow for typical black holes, it means that black holes are not eternal objects. They slowly lose mass over time, eventually evaporating entirely. The smaller the black hole, the faster it evaporates. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate, far longer than the current age of the universe. However, smaller black holes, such as those formed in the early universe, could evaporate much faster. As a black hole evaporates, it shrinks in size, and its Hawking radiation becomes more intense. In the final moments of its life, a black hole would release a burst of high-energy radiation, a cosmic firework display signaling its demise. The evaporation of black holes is a testament to the interconnectedness of physics. It shows that even the most extreme objects in the universe are subject to the laws of quantum mechanics, and that even black holes are not immune to the passage of time. Section 10. Myriad mysteries and unanswered questions. Despite our growing knowledge of black holes, they remain among the most enigmatic objects in the universe. Many mysteries and unanswered questions continue to intrigue and challenge astrophysicists. For example, we still don't fully understand what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed. However, the classical picture of black holes suggests that information is lost forever once it crosses the event horizon. This conflict between general relativity and quantum mechanics is known as the black hole information paradox. Resolving this paradox is one of the biggest challenges in modern physics, requiring a deeper understanding of both gravity and quantum mechanics. Another mystery surrounding black holes is the nature of the singularity. Our current theories break down at the singularity, suggesting that we need a new theory of quantum gravity to fully describe what happens at this point of infinite density. Section 11. The unending allure of black holes. Black holes, with their immense gravity, mind-bending physics, and potential to unravel the fabric of spacetime, continue to captivate our imagination. They are cosmic wonders that challenge our understanding of the universe and inspire us to explore the unknown. As we continue to study black holes, we are constantly surprised by their bizarre properties and their profound implications for our understanding of physics. They are natural laboratories for testing our most fundamental theories, pushing the boundaries of our knowledge and challenging us to think beyond the limits of our imagination. The study of black holes is a journey into the heart of darkness, a quest to unravel the mysteries of the most extreme objects in the universe. And while we may never fully understand these cosmic enigmas, the pursuit of knowledge will undoubtedly lead us to new discoveries and a deeper appreciation for the wonders of the cosmos.